There is a robot the size of a car driving itself across another planet right now, 140 million miles from help, carrying instruments nobody alive has ever seen returned, powered by a fuel so rare the United States nearly ran out of it. No one is steering it. If it drives off a cliff, the signal telling us would take between 3 and 24 minutes to arrive, and our reply would take equally as long to get back. That machine is the Perseverance rover, $2.7 billion of hardware that touched down inside Jezero crater on February 18, 2021, on a world that has never been kind to anything we've sent. Start with the simplest question: what is it actually made of? Its body is aerospace-grade aluminum, the same class of alloy used in aircraft fuselages, shaped on CNC mills to tolerances tighter than a human hair. Joints and suspension connections are titanium, chosen because it doesn't fatigue across the thousands of temperature swings between -80 and +20 Celsius in a single Martian day. Wheels are where it gets stranger. Earlier rovers used aluminum wheels, and the sharp rocks of Mars tore through them. Perseverance runs on wheels partially made from nitinol, a titanium nickel-shaped memory alloy that deforms around a boulder and springs back to its original shape, like the metal itself refuses to stay broken. That's the chassis. But a chassis weighing over 1,000 kilograms still needs to survive not just Mars, but the 7-month transit there, vibrating inside a rocket faring at frequencies that would crack most industrial equipment. Every component is tested in vacuum chambers, shaken on acoustic platforms, cycled through thermal extremes. Pulling it off takes thousands of engineers, multiple government facilities, and roughly a decade of sustained work. Which brings us to the power source. And this is where the story gets genuinely uncomfortable. The rover doesn't run on solar panels, it runs on plutonium. Specifically on 4.8 kilograms of plutonium dioxide sealed inside a device called the Multi-Mission Radioisotope Thermoelectric Generator, or MRTG. Plutonium-238 has a half-life of 87.7 years, meaning it decays slowly enough to be useful for decades while releasing heat the whole time. All of it gets converted into a steady 110 watts of electricity, continuously day and night, regardless of dust storms blacking out the Martian sky for weeks. Here is the problem for anyone thinking about rebuilding this. America stopped producing plutonium-238 in the late 1980s when the Savannah River site reactors closed, and by the 2010s the Cold War stockpile had nearly run dry. NASA was rationing the last of it. Production has since restarted at Oak Ridge National Laboratory, but the target output is just 1.5 kilograms per year, and each MRTG requires 4.8 kilograms. Building one rover's fuel supply would consume more than 3 years of the entire national output. Now assume you've solved the structure and the power. There is still a problem, though one that no amount of engineering talent makes easier, and it has nothing to do with metal or fuel. You cannot drive it. The distance between Earth and Mars shifts constantly, and at any given moment a radio signal takes between 3 and 24 minutes to make the one-way trip. A command you send the moment you see the rover heading toward a cliff wall will arrive at Mars somewhere between 6 and 48 minutes after you sent it. By then, the rover has already decided its own fate. This is why Perseverance carries a navigation system called AutoNav, built to make every major movement decision entirely on its own. Each Martian morning, mission controllers send a destination and a list of scientific priorities. Then the rover does the rest. AutoNav builds a 3D map of the ground around it, assigns costs to every possible path based on slope, rock density and sand, selects the safest route and adjusts while the wheels are already turning, with no GPS and no outside correction available. On a good Martian day it covers roughly 347 meters. Slow? By any measure. Extraordinary by any that matters. This is where the weight of the question settles in, because chassis and fuel and software are only the foundation. Chassis you could probably fabricate. Power you could barely source. Navigation software took teams at JPL years of iteration across multiple rover generations to develop. None of that is the hardest part. Hardest of all is what it's actually doing out there. Perseverance carries Cero on its robotic arm, an instrument that fires an ultraviolet laser at rock surfaces and reads the way molecules scatter that light, hunting for organic compounds that could be biosignatures of ancient microbial life. It carries PXL, which fires X-rays at patches of rock to map elemental chemistry in patterns that biology leaves behind and geology alone does not. MOSI ran 16 successful experiments converting Martian carbon dioxide into breathable oxygen, a proof of concept for infrastructure any future human presence would need. Each of these instruments required separate, specialist teams, calibration standards designed for a world we've never visited, and validation against chemistry that exists nowhere on Earth in the same combinations. Could humanity rebuild a Mars rover from scratch? Yes. But the answer carries a weight most people don't expect. Building one again would require tens of thousands of people, multiple national laboratories, years just to accumulate enough plutonium, and a decade of software iteration that can't be shortcut. Perseverance didn't emerge from a factory. What came out of JPL emerged from 60 years of funded, continuous planetary science, each mission passing its lessons to the next. Strip 60 years of institutional memory, of every lesson bought by every failed landing and every dead battery, and you aren't rebuilding a rover. You're starting the clock over. And somewhere out there in a crater that may once have held a lake, a machine carrying 110 watts of nuclear fire is making its own decisions in the dark. Alone, it has been doing this since February 18th, 2021. Nobody told it to stop.